The grade system, which I'll be describing to you today, resulted from a project that began roughly 3.5 years ago with a Montney player in northwest Alberta that wanted to get independent, third-party evaluations of bitware in their horizontal drills, which were roughly 10,000 feet down and 10,000 feet across. They found their bitware data of limited use because of the subjectivity and inconsistency of the data they were getting, as well as the fact that it offered no individual cutter results. As well, the photos of the dull bits they had were most often taken by cell phones, which suffer from lower resolution and perhaps more importantly, lower lens quality. There were also issues with lighting, focus, and perspectives on the areas of importance. At the time, they had 10 rigs or so running in close proximity, so we planned to locate the hardware at a central point in the field and bring the bits to that location. One of the first methods we looked at was handheld 3D scanning. We used a commercially available 3D scanning service to scan a dull bit. The results were reasonably good, but we concluded this method was not really viable because it required a trained technician to perform the scan. It took a significant amount of time for the technician to produce a good model, and the hardware was relatively expensive. Another project scoping requirement was that the technology developed produce cost-effective results. In effect, this meant that, in addition to low-cost hardware, the system could not require any additional manpower or special training to operate it. We also briefly investigated cell phone 3D scanning, which, although it sounds very appealing, was ultimately rejected too, because of the poor quality of the results. Taking all the requirements into consideration, it was decided to design and construct an autonomous system using photogrammetry to build 3D models. There were a number of reasons we wanted to focus on producing 3D models, rather than relying on high-quality photos, for example. Firstly, a manipulatable 3D model is far superior to a collection of photos for viewing. Just as a picture is worth 1,000 words, a 3D model is worth 1,000 photos. Secondly, 3D models are much better for assessing wear and damage to the bit body in addition to the cutters, and they are the only way to produce heat map comparisons to sharp bits. Thirdly, 3D models have significant advantages over 2D images when applying artificial intelligence approaches. And lastly, we thought if you're going to produce high-quality photos anyway, why not go all the way to produce a 3D model and reap all the extra benefits they provide? Phase 2 of the project included upgrading the software to include analysis of cutter wear and damage, more specifically, automatic identification of cutters and blades, cutter-by-cutter estimation of cutter volume loss, diamond table volume loss, diamond table face loss, and heat map comparisons of dull to sharp bits. Phase 3 of grades development involved the assessment of other parameters that might be viewed as judgment parameters, as opposed to the more calculable parameters in Phase 2. The software is now capable of analyzing for these parameters as well, with the accuracy of the results continuously improving as we scan more and more bits. The image on the right shows an individual cutter from a used bit. Here the software has identified the chamfer and the undamaged area on the diamond face, as well as the blue area which indicates this is a rotated cutter. And this is the area identified as wear. Here is another cutter where the software is identifying the chamfer and undamaged diamond face, the spalled region, and the worn region. This image shows a cutter indicating heat checking, a parameter that we are currently working on. Now, let's take a look at the grade software. Sean will run you through a quick demo.
Thanks, Ron. Grade, the autonomous AI-enhanced digital dull bit forensics system. A state-of-the-art system consisting of 3 components: a push-button autonomous robotic scanner, artificial intelligence engine, and an output software viewer. The user simply loads the bit into the scanner, names the bit, and presses go. The results include a high-resolution, isometric model that can be dynamically manipulated in all axes. In addition to conventional software tools, centering, screenshots, home, etc., you can also apply the cutter toggle to any of the heat mapping analytic masks, toggling on and off where the original cutters were located to gain a relative impression of the damage profile. The user can also select specific individual cutters on the bit model. in order to further review in detail in this side window. You will note the metadata table on the bottom corresponds to the selected cutter. The data in the exportable table is the output of the artificial intelligence engine, which locates cutters and blades and defines wear and damage. It also articulates the legacy IADC characteristics, such as lost cutters, delamination, heat checking, etc. Supplementally, grade provides a relative sharp to dull bit total remaining cutter percentage, remaining surface diamond percentage, and remaining total diamond table percentage. In addition to the raw texture map, there are 3 heat map masks that can be applied to facilitate forensic analysis. The robotic grade scanner yields results with metrological resolution in the order of 10 microns in order to provide the artificial intelligence with the data sufficient for precision. The graduated chromatic scale on the left of the screen shows step changes from blue, intact, to red, missing, and graduation of wear in between. The flat cutter wear heat map is used to accentuate surface wear. As with all the other masks, tool sets, and toggles previously mentioned, the model can be fully manipulated in this format. The wear by radius heat map is used to visually enhance surface body matrix striations to define where on the bit the work was done, nose, gauge, shoulder, etc. The last heat map mask is the absolute difference heat map, which again uses the chromatic graduated scale to precisely define the delta between sharp and dull bit, cutter by cutter, blade by blade, as well as on the body. The Grade Viewer software initially opens on this BitStacker archive screen. This graphical interface allows the user to readily visualize the defined wear and damage at a glance. Each section is a grouping by bit model type, with each individual bit run stacked chronologically on top of the others. Each individual cutter is represented by the squares running horizontally left to right. And again, the chroma scale represents relative wear. As is possible throughout the grade tool, the user can select individual cutters to compare cutter to cutter, bit to bit, by lithology, drill cycle, etc. In this case, comparing cutter 22 from one bit run to another. This can be done not only by wear volume, but surface wear, and of course all the other specified legacy IADC characteristics and enhanced grade wear characteristics. From this screen, you load any bit from your archive for analysis. Lastly, the Grade Digital Dull Bit Forensic System is flexible in that you can take high-resolution pictures for communication purposes and sharing. And the metadata grade table is exportable in order to be applied against EDR or other datasets for drilling dysfunction, root cause, forensic analysis. I will now pass you back to Ron to explain a little bit more about how to leverage the artificial intelligence and optimize drilling performance.
Thanks, Sean. So what's next? The IADC objectives for revisions to the grading system that were discussed at the beginning of this forum envision root cause analysis as an important aspect. We'd like to show a quick example of how digital dull bit forensics could enable this. On the left, we have data from the lateral portion of a horizontal well drilled in early 2020. The lateral was roughly 11,000 feet long and required 4 bits to finish. The dark trace is ROP, and the orange trace is a calculated parameter related to MSE, or mechanical specific energy. There were different types of bits run, and only bit number 2 was scanned. The scan data is represented by the column graph in the upper left, which shows the percent remaining diamond table from 0 to 100% along the vertical axis, versus the individual cutters numbered along the x-axis. This chart indicates a non-uniform pattern of wear, with significant damage to many of the cutters. Contrast this with the chart on the right, which shows another lateral in the same drilling program, where the same model bit drilled the entire 10,000-foot lateral, with low wear in a uniform distribution along the cutters, and no significant damage. Although we don't have time to go into detail in this forum, we postulate that a major reason for the shorter run in the first example was cutter damage caused by drilling dysfunction. By reviewing the types of damage seen in the cutter analyses, whether it be spalling or broken or chipped teeth, etc., along with the location of the damaged cutters on the bit body, that is nose, shoulder, gauge, we can begin to determine the types of dysfunction that caused the damage, whether it be stick slip, bit whorl, or something else. We can then correlate this information with EDR data to assess how we might prevent similar damage in future drills. In terms of the potential benefits to this approach, We estimate that the savings in bit trip costs between these two examples was in the order of $200,000 for the lateral portion alone. In conclusion, we feel that a digital dull bit forensics approach, such as the one outlined here, fits well with the work the IADC has undertaken to upgrade the grading system. Bit vendors and cutter suppliers can obviously use this data to review and improve designs, but the data can also be of enormous value to E&Ps seeking to improve performance by mitigating bit damage related to drilling dysfunction.